bioinformatician at the Kodram Institute. I work with Nabil in the core bioinformatics unit. And I will try to give you a quick tour of Nextflow and specifically the new version called DLS2. So our program now is to see an example workflow, to see what are the components of a workflow and what are the things that make workflow hard to write and to maintain. And then what is Nextflow and how it can help us writing better workflows. This lecture will be really focused on the practicalities on a small example rather than giving you a lot of theory. And the goal is simply to raise awareness on the importance of workflow managers in general. A next step can be to make you interested in learning more about Nextflow, maybe as a user, because there are a lot of nice Nextflow pipelines already available on the internet, but knowing how Nextflow work can help running them on your premises. And hopefully a small fraction of you will be motivated to try the hard path, that is to learn Nextflow and to use it for your future workflows. So let's see a typical workflow. This picture, this diagram comes from a paper, so it's a real-life example. We have some input files. Usually we have some FASTQ files from the sequencer, and sometimes we have databases or reference genomes or annotations. In this case, we have both. It's an RNA-seq pipeline, so we have both. Then in red, you have the tasks. So first you need to do the mapping, and then you need to reconstruct the transcripts, and to do the second task you need intermediate files that are generated from the first, and finally you have the pipelines output in yellow. Now usually you have a lot of input files, a lot of samples, and so the process needs to be repeated, or at least some processes need to be repeated, while other will collect outputs from all the previous steps. And different processes can have different requirements. Mapping is highly parallelizable, so you will benefit from having multiple CPUs, and if you have a cluster, you can send every sample mapping as a different job. Other tasks might be more memory intensive, so you're less likely to run a lot of them in your facility, but it's efficient to be able to specify the requirements in our workflow language. So this is the minimal example. Today we will try to write a small de novo assembly pipeline for bacterial genomes using the tools that you already know and that have been presented also by Anna before, like Showville for the assembly. So in the workflow here, you see that we have some input FASTQ files, and we have a set of them, so one or more samples. Specifically, we will work with paired and Illumina samples. We have a first block that is the filtering with FastP. Then we have the de novo assembly. We will use Showville, for example. And all these two steps are in a one-on-one relationship with the input samples. So you have 10 samples, you have to do 10 filtering and 10 de novo assemblies. We will use Quast to generate statistics on the assemblies, and that step will require all the assemblies to be finished in order to compare the metrics across all the samples. We can add optionally Proca to do some annotation, and Proca is a similar step, but it's going to produce multiple outputs. So in our vision, let's say, to see how workflow can be built, this means that some other blocks downstream might only need one of them. Maybe one block will use the protein FASTQ files, and another block will use the GFF. What we will need to solve is how to make the tool that we need available. As you saw, SnakeMake, for example, has a good integration with Conda or containers, and Nextflow works in a similar way. If we extend a bit the pipeline, we will see some other patterns that you might encounter in your pipeline development. So one is using MultiQC. MultiQC is a tool that I recommend you to use if you never did so. It's able to create an HTML report using multiple information sources, and it supports natively hundreds of tools. For example, FastP, Quast, and Proca can be automatically parsed by MultiQC, and some of their metrics can be gathered in the report. But what we will try to see is that if we add an extra step, for example, abricate for AMR prediction, and then we generate a summary, we might need, in our case, a custom script to create a MultiQC-friendly input. And we will see that Nextflow easily allows to add extra scripts in our pipeline that will work as they are installed in the system, or at least they are visible, they are exposed in the processes. And in the end, our pipeline will produce a nice report. Now, let me stress that this tutorial is an example to showcase how to write a pipeline using Nextflow, but we don't want to reinvent the wheel. So there are already great pipelines for the novo assemblies of bacterial genomes, and one in particular, Bactopia, bundles really a lot of tools, and coincidentally is also written, it's based on Nextflow, and the new version is based on DSL2. And there is a great documentation that I recommend you to have a look at to see what you can do. So what is Nextflow? Nextflow is two things. It's a language, it's a workflow language, so it allows us to describe the relationship between the tasks in a similar way as SnakeMake did. But it's also a runtime environment, so it's the program that can interpret the workflow and make it happen in different setups, from the local machine to the HPC with a scheduler, that can be Slurm or OpenPBS, and even to the cloud with Amazon Web Services or Azure or Google Cloud. So it's really flexible, and this is one of the advantages of using Nextflow, that this very good support of different environment is built in. And this happens also because there are basically two languages, if you want. One is the actual workflow logic, the main script, where you define the processes and the relationship they have. And the other are the configuration files. For example, in my HPC, I might have access to specific queues, for example, name or QIB long or QIB high memory or something like that. And this is something that you need to specify yourself, because every setup is different. But once you create your configuration file, for example, for your HPC, then you can reuse it with every other Nextflow script that you want to execute. So you separate the workflow logic and its configuration, which is, I think, a really good idea in general. Now, it's important that I warn you that there is a huge transition in Nextflow. The first syntax, called DSL1, is now becoming less popular because the new version is completely different, but offers massive advantages. Modularity, code reuse. You will see that the workflow is really readable. But when you Google for information or for help, it's good that you check which syntax the blog or the video is dealing with. So let's introduce some core concepts. The process is the description of the task. It's like a rule in SnakeMake. Specific idea in Nextflow are channels, because they are asynchronous queues, and it's around this data flow model that Nextflow was built. Basically, you create a channel, for example, with your input files, and Nextflow takes care of distributing the FASTQ files to different executions of the process that need them. And if your hardware allows for it, they are run in parallel, and you don't need to take care of that. It's going to happen magically. So finally, of course, there are the workflows. So a set of processes and channels is a workflow, and DSL2 allows you to create sub-workflows to make the code even more readable and reusable. So this is coming from Nextflow, the Nextflow website, and basically you can see that Nextflow allows you a lot of flexibility, because any programming language is well supported. Nextflow can orchestrate the job execution. It has tight links with Conda, Docker, and Singularity, and it's working really well with version control. And then there is the runtime, so the actual engine that will transparently execute your workflow in the premises that you have. And the small box is actually a screenshot of the execution runtime, where you can see that there are different tasks being executed. Some are pending because they're. To summarize, there is built-in support for containers, built-in support for HPC schedulers. It's very easy to scale up. If your workflow will work well and you need to analyze 1,000 samples, and this has been done, you can scale up and work in the cloud. Reproducibility, distribution, versioning is built in. And finally, there's a great community that will support you. And you will see some great example of the community with Robert during his talk later. Now, and I will stress again that the configuration of Nextflow is something that you need to take care as much as you take care of the scripts of the actual workflows. And it's working with an onion setup, so there are different layers. The pipeline will bring some configuration for itself, but you might have some base configuration, and then in your home directory you can have some other settings. So it's important that you try to familiarize with this idea and make small tests. But to make the simplest example, once you create your HPC Slurm configuration file, you can just reuse it and add it in your Nextflow run with -c that file. This is the simplest way, but it will be transparently included if you just put it in the right position. So let's move on with an overview of Nextflow. As I said, I will try to really focus on the examples to give you a taste of the process. So this is our pipeline. We will have as input a directory with paired and reads, and then we will have a fastb process to filter the reads, a showwheel process to assemble the reads, and then you can see that we have some tasks that will all need the contigs, and they will so be running independently one from the other. One is Quast. Quast will need all the assemblies to be finished because it's going to gather all the assemblies to make the statistics. Proca will be 101 running. As soon as a contig is ready, you can spawn a Proca process. Then we have Abricate, similarly, producing a file for each contig. Then we need to collect all the Abricate files and make a summary. And then, as I said, there is MultiQC that will collect a lot of files from different processes. So it's sort of a special thing. But as I say, as a pattern, it's good to think that every pipeline can be built with a nice MultiQC process at the end. In terms of syntax, this is the actual code. You can write a workflow that is really, really simple to understand. So this is the process, and these are their arguments. So in this case, we start with a reads channel. We will see how to create it. And then we run it. And automatically, this means run this process for all the items in the queue in the reads channel. And then assembly is a process that requires the output of fastb. In this case, we call it reads, so fastb.out.reads. And AMR will require assembly out, and Proca also requires assembly out. So this is not an imperative language. Proca can also start before AMR because they both need the output of assembly. So there is no need to run AMR before Proca. It's Nextflow will take care of understanding which processes can run and when. Now we see a pattern where Quast, for example, needs the output of assembly, but need all of them. Now, collect is the function to collect them, and this function means basically that the output is a tuple, so it's a sample ID and then the file, and we just want the file, so we will use the map function to reduce the queue of tuples to a queue of files. Similarly, Abricate will do the same with the output of AMR. And finally, MultiQC will mix a lot of samples, a lot of outputs. So we'll take the JSON file of fastb, and we will mix it with the output of Quast, Proca, and Abricate. And we will need to collect everything so that we will have a single process that will run when all the other channels are populated. Now let's see, this is the workflow. Let's see a single module, a single task. So this is, as I said, similar to snake make rule. This is the assembly process. There is an input section, an output section, and a script section. Now, every line in the input section is an input channel, and the process will create as many output channels as the lines in the output section. This is one input channel and one output channel. So we take an input channel with a sample ID and the actual reads, and the output will be a sample ID again and the assembly. So this is the bash code. Now, this is a tuple where path is a parent channel, so we'll have reads 0 with the forward read and reads 1 with the reverse pair. Then we have some other directives here. We can put the conda package to use or which container to use, but in this case we will just say that we want to actually put in the real output. So with publish directive, we say in the output directory create a assembly subdirectory and put whatever output the process will make. Sometimes we have multiple outputs, so we can name them to make it easy to collect the appropriate channel from in the workflow. So we say, okay, the context will be called ctgs, and the log file will be saved in the log output. To start, we need to populate a reads channel, and in our case, we will start from channel pairs. And to do so, we will use this pattern that means all the files that contains R1 or R2 and then end by fastqgz. This is the pattern to create paired end channels. If you have a single end channel, we just remove this curly brackets, and instead of from file pairs, you will write from file here. In general, when you have a channel you want to debug, the .view method will allow you to see its content. So it's something that you can use to practice and to work with channels. Well, we will see how to store processes in separate files. We will not see how to make sub-workflows, but it's a good idea. And in general, when you want to know how this works in Nextflow, the easiest way sometimes is just to write a very simple example that takes one input and makes one output, and you can use the .view method to see if the channel is what you expect or not.